Yeah, yeah. Can you hear us? Yeah, let me talk about forms with flat connection. And this is based on two very recent papers in the archive joined with David Gepner, Newton Kitchlow. And Newton in, and another joint with Newton in. So what's the idea? So the several ideas to look at cobordisms between single structures. And second idea, identify these groups. So identify cobordism groups with some familiar groups, and specifically we'll identify it in certain cases with the Grothendieck group, K0 of some category A, and in one-dimensional higher, we'll identify it with K1 group of a ring R. So K0, K1 are the first two algebraic theory groups of categories and rings, but this correspondence between cobordisms with decorations and cobordisms of single objects should extend beyond K0, K1, but for now that's what we've done. So let me explain. So let us first look at start with the category A. That's going to be abelian. So typical example is the category of modules over a ring R, but you usually need some finiteness condition on the category of modules. For instance, you might want to look at the category of finite length modules or finitely generated modules if R is Noetherian. And then the Grothendieck group, K0 of A. Sometimes it's also written as G0 of A, is an abelian group with generators given by symbols of objects of modules in A, symbols of M, where M is an object of A. And in example, that's a module over R of some with some size condition, so not too large. And whenever you have a short exact sequence of 3 modules, yes, yeah, boxes is like a symbol, so it's a symbol, so symbol of M. So M is an object, but we want to map objects to elements of an abelian group. So bracket denotes the kind of image of an object in the abelian group, or we can call it the symbol of an object in the group. And so whenever you have a short exact sequence of modules, we impose the relation that the symbol of M2 is the symbol of M1 plus symbol of M3. So for instance, if you take finite length modules, the modules which have a finite filtration by submodules, so example, finite length modules, length modules over ring R, then modules finite length, if it has a filtration, finite length filtration such that I over mi plus 1 are simple. Then if you denote the set of simple modules over R by L sub j, j is in some index at j, so for every simple module, it's isomorphic to a unique module on this list, in this set, then the sort of the symbol of M is the sum of the symbols mi over mi plus 1, or I. So each of this is isomorphic to exactly one of the LJs. So this becomes sum over symbols of LJs with some multiplicity in J, finite sum, J is in J, and J is in Z plus. And this allows you to identify in this case, you identify the Grothendieck group null of this particular A with 3-abelian group on the set of isomorphism classes of simple modules L sub j. So Zj so as the basis of these elements in the graphene group. So that's one example. And as maybe as an exercise, compute k null of the category of Z modules in two cases. This is finite length modules, and second case, finitely generated modules. You'll get different abelian groups in this example. And K null, I mean, for me, I mean, K null appears a lot in verification, where you have some integral system, and eventually some of the abelian groups that you see in the system become graphene groups of some interesting categories. And homomorphisms between these abelian groups, they live two functors between these categories. So that's very common in verification. This is my personal interest in K null. So sometimes you just see the structures, and turns out there are categories and functors behind these abelian groups and linear maps between them. And in fact, in verification, you kind of see just K null, and you don't see K1. But let me now explain how you can think of K null topologically. So we claim that K null of A can be identified with some kind of cobordism group. Well, let's understand this. So let us first start with zero manifolds. Let's take a point that's a zero-dimensional manifold. Let's give it orientation plus or minus, and we're gonna decorate it by an object of this category. So we decorate a point by an object of A, and a sign. And next, we're going to look at, so we can have several points. Let me just draw them on a line, several points with plus or minus signs and decorations by M1, Mn. And I want to look at these collections, modular cobordisms between them. So let us think about what are natural cobordisms. And I want to get these collections, modular cobordisms, I want to identify it with K null of A. So here are the cobordisms we allow. We can take a point, plus and minus, and decorate both points with M. Then there's a cobordism, which is an arc with orientation. Orientation is chosen so that it induces the corresponding orientation on the boundary, plus or minus. And you should think of M as being carried by this arc. So you can think of having a trivial bundle over this arc with fibers M. This is cobordism into nothing, and we want to say that this means that this collection is cobordant to the trivial object or trivial empty decorated zero manifold. We can have these cobordisms. But what of course, we want to say that this cobordism corresponds to the relation of the graphene D group with the symbol of M, because you take this point, it carries M, so symbol of M with plus, a plus sign. This is a point which carries M, but with a minus sign. So we want to think of this cobordism as giving us the relation with M minus M is 0, which of course just a relation in abelian group. Yes.
Is that in definition, the symbol being symbol of M2?
Yes, yes. So in fact, by definition, yes, by definition, K null is an abelian group with these generators, symbols of M, and defining relations. They're all obtained as follows: for any short exact sequence, we impose the relation that symbol of A is the sum of symbol of M1 plus, so symbol of M2 is symbol of M1 plus symbol of M3. So we just impose those. Yeah, those relations. Yeah.
So I didn't understand the bundle. So are you saying that we are taking zero dimensional manifold and it has a bundle?
Yeah. Yeah, so we sort of want to think of this arc in formula. So over every point, there is a copy of M. And there are isomorphisms as we follow along this path, this arc, there are isomorphisms between them. So you don't think of this as a flat connection over the interval with fibers M. But of course, because the interval is contractible, the flat connection is just trivial. It's just the product of the interval and M. But we're not trying to make this too precise. We just kind of, but I think this is kind of intuitively clear that we can say that we fix isomorphisms between the stems over various points which satisfy obvious compatibility relations. Okay, and let us also try to interpret this relation in the language of cobordisms. So let us say if this is plus with M1 plus with M3. I'm going to put here plus with M2. I'm going to look at a singular cobordism. So the singular cobordism, we keep track of orientations. So let us we think of this interval as carrying M1, this interval as points as carrying copies of M3. To remember which one is first and which one is last, in the short exact sequence, we put an arrow from the first to last. So we think of this point as sort of encoding as remembering a short exact sequence. So in other words, over usual points, over regular points, we just have a copy of M times the interval times its neighborhood. But at this point, we remember short exact sequence M1, M2, M3. So when we talk about a flat connection over a graph, we agree that at this vertices of a trivalent vertices of a graph, we remember the data that we're given as a short exact sequence. And so we should probably agree which one is first, which one is last, to remember the order of the terms in the sequence. And this is how we think about how we define flat connections over a graph in this case.
It's not the same thing as one.
Sometimes, in some cases. So there is a version. So I mean, because eventually we'll mention, we'll need this if you look at the category of projective modules. And if the modules are projective, then if these are projective, so then a short exact sequence splits. So if modules are projective, then there exists a splitting. P2 is P1 plus P3. And then there's a version of this construction where we just, again, it's up to us. We can agree that at the vertex, in this case, we remember. You can agree that at the vertex, we remember a direct sum decomposition. And that is stronger than a short exact sequence of projective modules. That's more data.
I think we can say that the short exact sequence is not in between.
Yeah, so we want to say, in fact, in this, we only care, it's kind of a little bit, in some sense, we even agree that this just tells us that this, we think of this as zero manifolds with decorations, so decorated zero manifolds. Decorated manifolds. And we just say that they're cobordant. That there is a cobordism from one to the other. So a cobordant. Yeah, this cobordism, well, it's given, let me say it like this, is given by this graph with decorations. But because in this example, our graph is very simple, it's just the vertex is given by a short exact sequence. But you can imagine cobordisms which have more complicated graphs. It's kind of up to you. You can decorate by various, M1, M3, M5, M6, and this would be M2 and M4, and you have short exact sequences. Just an example of a more complicated cobordism. So here we could, so we can now identify, we nullify with the cobordism group Well, we can put some labels, cobordisms that carry data from A. Let us call this a cobordism between zero-dimensional manifolds. Let's say cobordism 0 of A. But again, so cobordisms are these graphs with data. Yes.
So, for example, R modules, then between any two R modules, I mean, it's not always true that if the short exact sequence is split exact there, right? So it's not always true that.
Sorry, for projective modules, I'm just saying that there are variations. I mean, I'm saying that there are variations on this construction. So, in fact, for a ring R, there is a notion of k-null of a ring R, and in k-null of R, the generators are symbols of finitely generated projective module, and relations are whenever there is an isomorphism between a module and a sum of projective modules, then P2, symbol of P2 is P1 plus P3. Of course, for projective modules, having an isomorphism is the same as having a short exact sequence for projective modules. So if this module is projective, you can find this section.
Yes. And you were saying that even in general, that has to go through for calling this as a short exact sequence.
Yeah. So for projective modules, this is how we define k-null of a ring R. Well, this is how we define k-null of a ring R. So I'm distinguishing between k-null of a ring and k-null of a category. And maybe a better name for this is maybe g-null of a category. Yes. Yeah, this just means that we're looking at some. This is informal, so we didn't give it. But so this means we're looking at cobordism classes. Cobordism classes of decorated, of A decorated, oriented zero manifolds. But and this is very easy to see just from what we've discussed, because when you have such a cobordism between A decorated oriented zero manifolds, it's built out of this, by definition, it's built out of this trivalent vertices, and then this U-turn cobordisms in either direction, and they match the two types of relations. This relation that you have in any group, in any abelian group, and these relations that you have in k-null of a category. Yes, and then up like this, m carrying m. This is going to be m plus, m minus. So again, it's the same relation. Symbol of m minus symbol of m is 0. And again, it's sort of not a it's not a big deal, but it's just kind of a cute remark that we can think of k-null in this way. Yeah, there is also something called Grothendieck semigroup. In a Grothendieck semigroup, you have these relations, but you don't introduce minus signs. So you just have a semigroup. You can add, you can also subtract. Then we get the Grothendieck semigroup. Let me actually call it something. Maybe I'll call it K0 plus of A. So this is Grothendieck semigroup. So it has addition, no subtraction. Then we should just disallow subtraction. So then everything should be a plus, no minuses. Everything should just go up. So we look at cobordisms that only go up, or that can split and merge, corresponding to those trivalent vertices. So we would have a cobordism. We'll have a cobordism like this, where everything goes up. And then we would look at these points, which all carry plus with labels M1, M2, M3. Module with cobordisms, and that will give us an interpretation of the Grothendieck semigroup. But I mean, all of this is just a trivial remark, but the idea is to try to go into high dimensions. So let us look at K1. Let us recall one of the definitions of K1 of a ring R. So that's an abelian group. Now it's not for a category, for a ring R abelian group. And generators are pairs P and alpha, where P is a finitely generated projective R module. Let us say that we always consider left modules, so finitely generated projective R module. So it means that there exists Q, such that P plus Q is isomorphic to R to the n plus some n. And alpha is an endomorphism of P. And these are the generators of K1 of R, and the following are defining relations. There are two types of defining relations. Suppose that alpha and beta are automorphisms of P. Then we say that P alpha beta is P alpha plus P beta. And second, if you have a short exact sequence of projective modules, and you have a compatible triple of automorphisms. So I'm going to copy the sequence below. And there are three automorphisms, alpha 1, alpha 2, alpha 3, which make this diagram commute. And we also impose the relation that P2 alpha 2 is the sum P1 alpha 1 plus P3 alpha 3. So two types of relations. So let us try and so maybe one thing to remember is that P1 of R is closely related to determinant of invertible matrices or invertible operators. So the point is that, for instance, as P, we can take Rn. Let us even make R a field, okay, field. Then necessarily P is Kn, and alpha is an endomorphism. Kn, so it's an invertible linear operator. Then it turns out that in this case, a K1 of K, field K, can be identified with K star, where we send a pair Kn and alpha to the determinant of alpha. So the K1 group is very closely related to determinant of a linear operator. And its version, its kind of generalization for other rings other than fields. And so that's. But sort of we claim that this can be, there's some connection to such cobordisms, but we need to go in one dimension higher. So let us think about this pair P alpha. So we have a point. So here we had a point, and to a point we assign object M or assign a projective module P. But here we have a projective module with endomorphism alpha. So let us take a circle. Let us over a point of the circle put P, and then put a copy of P over every point in the circle, but so that as we go around the circle, we create an automorphism, create a monodromy. So we put P, but as we go around the circle, we create an monodromy. So an example, maybe let us take as an example R to be Z. So over a point, we put a copy of Z as a module over ring Z with endomorphism -1, just x goes to -x. That's endomorphism of the module, but not of the ring module. Then we can take Z and put a copy of Z over every point, but as we go back, we send x to x comes back to -x. This is sort of Z version of the Möbius band. The version of the Möbius band. As we go around, x goes to -x. Okay, so that's so now we're starting with now to this pair P alpha, we are assigning one manifold oriented because we want to know the direction of the which we compute monodromy plus a bundle over it, bundle with fibers a projective module, and it's flat bundle, so we can move in its fibers locally. Okay, now let us interpret. Now, so instead of 0 manifolds, we're working with 1 manifolds with a flat connection over them. But here we're taking this manifolds modular cobordisms. So presumably here we should look at this manifolds modular cobordisms as well. So let us interpret these relations now. So we have a cobordism from as a Pence cobordism from 2 circles to 1 circle. So over the circle we put P. So here we put monodromy alpha. Here we put monodromy beta. Here we put monodromy alpha beta. But so then that's perfect. So if you want, you can kind of trivialize over this kind of this cut or this cut. Everything is trivial. But here monodromy is alpha. Here monodromy is beta. And they merge these two pants merge. I mean, these two circles merge into one. And the monodromy along this top circle is alpha beta. So we're interpreting this relation in K1 as saying that these two are cobordant. This is P. This corresponds to P alpha. This corresponds to the element P beta. This corresponds to the element P alpha beta. This one is dotted line. This is just to trivialize because it's saying that over this dotted line, the P's are identified and they're identical. So over this dotted triangle or the dotted tripod, I call this a tripod, all the fibers are P's and the monodromy is standard. There's no monodromy. It's as you travel along this line, it's identity. Flat connection is identity. Flat connection is identity. But as you go around here, it's alpha, beta, and alpha, beta. Okay, so that so now what about these things? So the idea is to start with this diagram of a tripod. So put here P1, P3, P2. And that sort of tells us that there is a short exact sequence. And now sort of multiply by a circle. Multiply by a circle and not monodromy. So let me try to draw this. So what we have at the top is P3 with monodromy alpha 3. Here we have P1 with monodromy alpha 1. Here we have P3 with monodromy alpha 3. So what we're saying is we want to consider the following form where we take this tripod, multiply by a circle, and we add monodromies. So here monodromy is alpha 1, alpha 3, and alpha 2. Alpha, let me see, P1. This should be P2. Yeah, P2 and alpha 2. And alpha 2. So this is our cobordism between the union of the circles with P1, P3 to the circle P2 alpha 2. So we sort of introducing forms. That's why the forms in the title. So we want to consider singular two-dimensional cobordisms between in this case it's one manifolds. And so the idea is that the category of such cobordisms, COB1 over R, should be isomorphic to K1 of R, but we'll need to clarify this a bit. But also just to show you how you can interpret this defining relations using cobordisms between singular cobordisms between one manifolds, and everything carries a flat connection. But then with understanding that along the circle we can have on the facet 1, we have P1 monodromy alpha 1, P3 monodromy alpha 3, P2 monodromy alpha 2. Yes, yes. And here so cobordisms have to be singular. So now, what does it mean? So here we have a singular, what we call it, a seam, singular seam. But imagine that you intersect this cobordism by a plane in a different way. Then you'll see some kind of singularity. So the idea is that we actually want our one-dimensional objects to be not just circles, but allow more general singular manifolds. So for instance, we would want to have a picture, allow a picture like this, where, well, let me draw a bigger picture. So we should, for instance, allow cobordisms between singular one-manifolds. Those are called one-forms, forms of singular one-manifold with some data. In this example, the data should be something like, if you put here over this point, if you have projective module P2 as the fiber over this point, P1 and P3, P1 and P3. Then at this point, if you just care about direct sum, you would want to have a decomposition P2 is isomorphic to P1 plus P3. But then over this point, we also need a direct sum decomposition, which doesn't have anything to do with this one, P1 plus P3. So then a flat connection over this form should be encoded by this data pair of isomorphisms. Or you can just say it's encoded by modules P1, P3, and automorphism P1 plus P3. Automorphism is itself given by the composition. This isomorphism followed by this isomorphism. And also, if you're looking at cobordisms between these one forms, then it's natural to allow vertices in our cobordism, because when you look at singular two-dimensional structures, you see not only singular seams, but you see singular vertices where things come together like this. So from the viewpoint of flat connection, you would want to put, say, P1, P2, P3 on this facets and put here P1 plus P2, or an isomorphism between some of this and P1 plus P2, isomorphism here between this and P2 plus P3, and P1 plus P2 plus P3. I'm just writing this in a shorthand notation, but you should say put here an object, isomorphisms. So every seam gives you an isomorphism between the three objects with some compatibility relation. Yeah, so you need to. In this case, if you're doing direct sums, you don't need to put little arrows because then we don't get it. But in this case, the orientations must be compatible. So maybe I'll skip those. But so the orientation should be orientations. I'll just draw it for this form. So if you put in here P1, P3, and P2 isomorphic to P1 plus P3, orientations should match, meaning that orientation from the smaller carried from the facet that carries the smaller object should flow naturally into the orientation of the facet which carries the bigger object. So they flow naturally into here. But on these two facets, they have opposite orientation. Same as for in one dimension. In one dimension, this orientation flows into this orientation, but these are opposite. These diagrams are so actually we'll need to put these diagrams on the plane, and we'll need to put cobordisms between them in free space to get the match.
Yeah, that's what I was. And here also, I believe things are embedded, or are you working with?
You can do here in this case. You can do either. You can do embedded. You can also allow intersections. Just intersection. Nothing happens at the intersection. You just modules go through each other. So M1, M2, they just go through. It's like a virtual intersection. Nothing happens. You can allow that.
Ask differently. So what's the morphism?
Here, yeah, it's morphism is built out of morphism is one form from an oriented zero manifold with these decorations to an oriented zero manifold with these decorations. But your one form has a decoration, has a flat connection. Flat connection so means kind of what we naively understand by flat connection along edges, but also at the vertex, it's either a short exact sequence or a direct sum, depending on which version of the story we're considering. So the vertex is either short exact sequence or direct sum decomposition. Okay, so to make this more rigorous, it turns out that we need, for this isomorphism, we actually need to put one forms in R2 and cobordisms between them in R3. So we kind of, so our forms will, one forms come with all these decorations. So specifically, we're gonna, edges are decorated by projective modules, and vertices are decorated by direct sum decompositions. And if we just have a circle in the plane, then it's decorated by projective module over the point, and there's a monodromy, so there's endomorphism alpha along the circle. So for instance, if you have a circle with fiber P, suppose that automorphism is trivial, then it's actually null homotopic because I can cap it off by a disk with a trivial connection, because then the connection extends to the connection on the disk. So then it's coordinated to nothing, so it's null coordinate. Just an example, which is of course matches here, because if you put identity, you see that P identity is 1. I should also mention an equivalent, a second description of K1 of a ring. So let us take our ring R, consider Rn, and an automorphism Rn Rn is given by a matrix A of size n with coefficients in R. Let us, and the matrix is invertible, so actually A is in GLN R. There's an invertible n by n matrix with coefficients in R, or just automorphisms of Rn. And you have a inclusion GLN R sits in GLN plus 1, GLN R. GLN R sits in GLN plus 1, and plus 1 R. So you get bigger and bigger groups, and this inclusion sends A to A and one unit matrix, zeros. So you can take the direct limit denoted by GLR, the union of all these groups. An element here is just a matrix A that's some size n by n, and then you have infinite chain of ones without touching something. Okay, and then so you can take the commutate. You can take the commutant GLR. That's a subgroup. GLR. And then there's a theorem that K1 of R is just the quotient. It's GL of R modulo the commutator subgroup of R. How do you match this definition with that definition using projective modules? So for instance, if you have if projective module P is Rn and it has endomorphism alpha, then alpha gives us a matrix A in GLN R. So we can send this pair P alpha, send it to A, and then to its image in K1 in the quotient, in this definition of K1 in the quotient. If P is not projective, then you can complete it to a free module. If P is not free, if it's projective, you can complete it to a projective module. Then you can take an endomorphism alpha, written as a matrix for P, on Q its identity. This automorphism of P plus Q can be written as a matrix. I'm schematically writing this matrix in this way, but it's actually some other matrix. I'm schematically writing it maybe better to say it's alpha here, identity here. This is the morphism of Rn. Write it as a matrix and send P alpha to that matrix. Let me, so P is finitely generated projective, so you can complete it to a pre-module. Okay, so without more details, let me just say that this is another way to define K1 of R. So let me show you how to map a form. So with this flat connection in the plane. Let me do an example. So let's take this form. It has flat connection, so all these projective modules, direct sum decompositions, and it has to be in the plane. And I'll say more and give you more reasons why later. How do we map it to an element of GLR module of the commutator? So the idea is to, well, let us cut it into pieces where every piece is kind of constructible. Let me, for example, choose the system of cuts over these points. Let's say you have fibers P1, P2, P3, P4, and our form is oriented. So in this example, it breaks into 3 pieces. So if you remove the points, the marked points, you have 3 pieces. 2 of these pieces are tripods. You remove these 4 pieces. 2 of these pieces are tripods. 1 piece is an interval. And if you just look at one of these pieces, let me just look at this piece, for instance. We're going from P1 to P2, P3. And we have a decomposition. P1 is isomorphic to P2 plus P3. If you look at this piece interval from P2 to P3, then the flat connection is an isomorphism. So let me in fact call this maybe for every piece, excuse me, for every piece, let's call it for every piece maybe J. I have an isomorphism F sub J, isomorphism from 1 or 2 projective modules to 1 or 2 projective modules. So this is F sub J. Then F sub J here is a sum from P3, P4 into P1. So now let us take the direct sum of all the PIs. Take the sum of all these projectives. And so set up a map F from this sum to itself is just the sum of Fj over all J. Notice that at every point there's one arrow going out and one arrow going in. So at the outer will correspond to a map from P1 to P2 plus P3. Here an outer will correspond to a map from P2 to P4. There will also be maps back in, like sort of map from here from P1 to P2 plus P3. There's one map in. Just take the sum of these maps. And in the first approximation, that's what we want to assign to, let me call this this one form before the data gamma. So to gamma, we want to assign so F, what is F? F is an automorphism. It's automorphism of P, where P is the sum. Well, F is clearly a map from P to P. Why is it automorphism? Because you can just reverse all the arrows, and write the inverses of your maps. And if you go back and forth, you get the identity. The F inverse is well defined. So together we want to assign P with automorphism F. You can write it as a matrix once you complete P to a projective module, to a free module. Okay, this is almost the right answer. But so you discover that if you change the number of points, that every time you add an extra point with some fiber P sub K here, you can discover that you're actually changing the image. Again, you assign to the projective module and automorphism F, and it maps here into this quotient. But you can check that if you add a point, you're doing some minor modification to this element, to the image of this element in K1 of R. Namely, adding a point here, adding an extra point, forces you multiply the automorphism by the matrix 0, 0. This is your P sub K. P sub K, two copies of the same projective. Okay, 1, 1. So you're adding a transposition matrix. And this transposition matrix, or maybe I'll just say that for any projective Q, this transposition matrix defines an element, what I call it tau of Q. It's an element in K1 of R. Again, we're taking this matrix and then looking at the image in the group modulo the commutator subgroup. So I'm denoting the image by tau of Q. Its image there, and it might be non-zero because if R is a field K, then K1 of R can be, K1 of K can be identified with K star. Just take the determinant of this matrix, and Q is just K. Then it's this matrix with determinant -1. So here you could get a non-trivial element of K1. And in fact, you can of course from this you see that tau Q can be non-trivial, but it's always an element of the two torsion subgroup, which let me know by K1 2 sub R, K1 of R sub 2. And tau, so tau is a homomorphism from K0 of R into K1 of R. And the image lies in the two torsion subgroup. So it turns out that this is not quite the right thing to do, because you get a well-defined element up to elements from this image, up to elements from tau of K0 of R. So we need to twist a little bit, but just slightly. So what we should do, we should multiply by the tau of P. That kind of untwists it back to what we want. But there's still a little bit to do, because if you now take a circle form in the plane P and monogamy alpha, then because there is this point, so we'll have the usual P with automorphism alpha, as this is what we want to get for the circle. To the circle, we should assign this pair P alpha, its image in K1 of R. But we actually twisting it by tau of P, because there's a point here that we chose, and B, so there's modulo P, so we multiply by tau of P. So we need to further untwist it. And the way to do it is to take our diagram, and so how can I untwist it? We have this caps and caps. The diagram have this local maxima and minima. So this one has few local minima to local maxima. And we add a term for this local maxima and minima. So let me see. So the terms are, there's some freedom here, but let's say this is, if this carries P, we add tau of P. Then because this is isotopic to identity, you should put its inverse two torsion, so you can just put tau of P, put here 1 and 1. So add this, let me call it tau tilde of gamma, additional term, which is a product of all local maxima and minima of either tau of P, where P is the fiber of this point, so 1. This is just to further untwist it, to get rid of the extra term when we have a circle with a dot, with one dot to measure things. And this turns out to be an isomorphism. So take a planar form with this flat connection. And again, points, fibers of flat connection are finitely generated projective modules, and vertices we have direct sum decomposition, and form is embedded in the plane, and send it to this expression, and we get an isomorphism. So theorem. So theorem, let me write theorem like very in a compact way, saying a cobordism group of forms that carry this kind of flat connection one forms embedded in the plane modulo cobordisms. I'll give you an example of a cobordism. For instance, let's just a piece of the form. These are orientations. This is P1, P2, P3. Here, this object is isomorphic to P2 plus P3. This object is isomorphic to P1 plus P2 plus P3. So there is a cobordism to this P1, P2, P3, P1 plus P2, P1 plus P2 plus P3. So there's a cobordism which creates a vertex. So if you look at cross sections of this of this form by the planes near a vertex, then you'll see two of these pictures. So that's for an example. There's a cobordism from here to here, which creates a vertex. So if you pick the singular cross section, then you see this picture at the cross section. Well, let me give you another example of a cobordism. So we're going to start with this form. So we want to go from this form to this form. This is P1, P2, P1 plus P2, P1 plus P2. So, I mean, strictly speaking, I should put different labels here and say that there's an isomorphism between this module and this sum, and from this module to the sum. Let me just, for shorthand, write it this way. Then there is a cobordism here, which is sort of like a singular cap, singular cup. It's a singular cap. There's a seam here, and this is P1 plus P2. Another thing, like if you have a line, for instance P, you can split off. You can do this cobordism, which splits off any automorphism you want. Any automorphism you want from P, so any automorphism alpha, but this automorphism is multiplied by alpha inverse. So you can do things like that. Yeah.
So
Which?
Tau
tilde. Tau tilde was just a name for this contribution. So we sort of, the point is that this is not quite the right answer, because we're getting extra terms of this form. So we untwist them by multiplying by tau of P. But this is still not quite the right answer, because for a circle with a single dot, we're multiplying what we want to have by tau of P. So we need to further untwist it, so we put the form in the general position relative to the height function, and then we we look at local maxima and minima. So for instance, this is 1, this is 1, but this is tau, we will multiply by tau of P2. So let's say carries P2, and multiply by, what's the other one? By tau of P3. Yeah, so that's so in our paper we went as far as K1. Now if you don't embed your form in R2 in the plane, just have a one form, then the issue is that you can kind of have this circle P with monodromy alpha, but you can also, or even with identity monodromy, or you can have this, the same circle, but you can draw it differently with this intersection, and this intersection will contribute tau of P. So if you don't have an embedding, if you don't work with forms embedded in R2, then the group will be identified with K1 of R modulo the image of K0 of R by tau. So for example, if R is a field, okay, then instead of just K1 of R, which is K star, we'll have K star modulo plus minus 1, because over a field, any projective module is free, and then you get minus or plus 1 as this, so then you get this as your cobordism group. So we wrote up the story mostly up to K1. There's also some way to interpret this isomorphism by looking at Quillen's, one of Quillen's definition of K theory using homotopy groups of the classifying space of some category that we built from a category of modules. Then taking classifying space, kind of building some kind of codimension one picture in the space that resembles the form, and then K1 of R. I'll just mention this very briefly. K1 of R can be identified with pi2 of the classifying space of the Quillen category, of the classifying space P of the Quillen category, QR. And so in the classifying space, you can draw some kind of codimension one form, and then under this map S2 into the classifying space, you can take the inverse image of that one form, and then you see something similar. You'll see, start seeing these pictures in on your two sphere. And this is sort of one way to interpret this story. But we're seeing these forms from the map into a classifying space. But so our hope is to get new flavors of K theory by looking at forms with various data, unoriented forms, so forms with a framing, or forms mapped into some topological space, or forms embedded into something else, into higher dimension vector space. So the hope is to kind of just get new flavors of K theory out of this. Of course, K theory is like it's highly developed theory, so it's hard to say something new. But something, of course, there's always hope. And then there's also a paper where we do something similar in the non-additive case, where instead of exact sequences, the replacement for an exact sequence is something non-additive. You can just take an interval and break it into two pieces. And so take an interval of length A plus B and break it into two pieces, A and B. A and B. You can kind of draw this by saying we break an interval into these two pieces, A and B. And then we can build a global object out of this, which is sort of, it's one-dimensional in this direction and one-dimensional in the orthogonal direction. And you can encode the other direction by just saying this is thickness A, this is thickness B, thickness A plus B. And then you can look at this object's modular cobordisms. Do something like split here into A and B. Then you can permute A and B and merge them again. A plus B. A. And look at global objects built this way. And then we interpret. So people studied the dynamics, where you take an interval, break into several pieces, and reassemble the pieces. Those are called interval exchange transformations. So we look at slightly more general things where you can have a one form with this thickness, and you can think of this kind of distributed version of this kind of break and merge. And we identify the cobordism group of this form with K1, cobordism group of this form with K1 of something called assembler due to Ina Zakharevich. And that K1 turns out to be large. It's RHR over Q, a sort of exterior square, but over a much smaller subfield. So this ends up being very large, and the up to cobordism, the image of this form would be A which B, or this is thickness A and B. And then so you can kind of do the sort of non-additive analog of exact sequences, break an interval into pieces. And again, this is a toy model, but I think there is potential to further develop this into some kind of looking at cobordisms between singular structures, cobordism groups between single structures, identifying it with perhaps flavors of K theory or something else. Well, since I mean, unfortunately, I don't know the theory, but there's kind of homotopy type theory where you study types, proofs, etc. So maybe there's some way to put types on facets of the form, proofs on facets of the form, and can study cobordisms. Maybe let's make some sense. I think there's potential to further explore this story. I think it's maybe a good time to stop. Thank you.
Abstract or in your papers, you mentioned cobordism hypothesis.
So cobordisms.
Cobordism.
Oh, yeah, maybe. Yeah, I think this is sort of, for now, this is simpler than, I mean, it's more elementary than cobordism hypothesis.
Sorry for the paper.
Yeah, I think we mentioned it, I think, in one of the, but I think at this level, it's much more elementary. This is all kind of can be done by hands without fancy machinery. I think if you want to do this in all dimensions, then you need various tools, like serious tools.
So with, during the second half of the talk, when you're focused on the K1, that was all for these projective modules. But I think you're kind of alluding to this. Does your description also work for the K theory of exact categories?
Yeah, I think so. Yes. So if you instead of projective modules, you pick an exact category, exact category C, then you should be able to repeat all of the story. So you put flat connections, so you put objects of C on your, again, I think for isomorphism with K1, you think you want to look at forms in R2 carrying sort of flat connection with where you put objects of C. So at the vertex you put this exact sequence in category and look at this modular cobordisms. And I mean, that should give, so we didn't check the general case for K1, but I think this should give you, you need to, if you're on the plane, you should probably just have some convention that this is always in the plane, that you always go from the leftmost to the rightmost. You, in other words, just fix the convention so you don't draw these pictures. But otherwise, I think you should get K1 of the exact category in this case. In fact, K1 of exact categories, they have been studied by Nenashev and Sherman, and they have generators and relations for them using actually pictures like this. So using pictures like this. So you have a pair of exact sequences, one and another. So this is M1, M3, M2. So at each vertex you have an exact sequence. So if you look at Nenashev's work, he exactly describes K1 using pairs of such exact sequences. And in related work by Sherman, he does something similar, where he describes. I think he shows that K1 is generated by pairs of exact sequences M1, M2, M3, where you have a sequence in one direction and you have a sequence in the other direction. So you kind of have these orders, but the orders are reversed. This is M1, M3, M2. This is M3, M1. So you need two sequences in opposite directions. And here you just put this to interpret as a direct sum. You kind of create a direct sum of M1, M3, and then open it up from the other side. So you can interpret Sherman's pairs of oppositely directed pairs of exact sequences using these pictures.
Do you have any conjectures about things that you still are?
Yeah. I think we can. One would expect that this works for high K groups, but I think the interesting thing would be to explore, just look for new flavors of K theory. And again, so much has been known about K theory starting from 50 years ago, from the discovery of higher algebraic K groups. So it's an incredibly well-developed area. So I'm not saying, I mean, who knows? I mean, perhaps sometime in the future this can be used for computation, but it's already, things already very computationally advanced. So right now, I think the best bet is maybe get new flavors of K-theory. Another question is whether some version of this can be related to dynamics, whether cobordisms between singular structures can be useful for understanding some dynamics. I think that's because here we have dynamics of interval exchanges formations, some small piece of it rethought from the viewpoint of cobordisms.
So when you're looking at K0,
Yes,
do you have a
yes.
description? Like, so let's say you work with modules over a community ring.
Yes, yes.
Product?
Yeah, you have tensor product for commutative ring. You can take tensor products of projectives. Yes, for commutative L. So if R is commutative, then you can tensor projectives. You get the finitely generated projective. So that means that K null of R, null of R is a commutative ring. So you have a little bit more structure. If you want to tensor product, yeah, I should. Yeah, you can try to sort of. I mean, you can try to kind of have a different kind of vertex where P and Q, where you pass to the tensor product rather than direct sum or exact sequence. But it kind of feels a bit contrived. But I mean, naively, you can try to have a different kind of vertex where you pass to the direct sum. But I think on this kind of, but it doesn't feel kind of the right thing to do. So I think there is, it's not clear how to use this kind of pictures and cobordisms to interpret when you have both addition and multiplication. And I think I don't see a good way to interpret them both using cobordisms. But I think it's a very good open problem, but it's a very informal problem.
So in other words, hear me out. Like, so instead of just P and Q as being one in, you could have 2, 3 in. Two lines, 3 lines, and you check every.
Yeah, so maybe for natural numbers, maybe. I mean, to me, I mean, I thought a little bit about this, and suddenly I feel like that, you know, if it's just plus, we can do it using cobordism, so to speak, and multiplication. Maybe we can use cobordism, but both, I mean, do it both naturally. It seems to be very an issue, and one can explore what Scott just said. But it's just not clear how to interpret this. It's like such a simple structure of a ring or a semi-ring, but it's not clear how to do from this viewpoint of cobordisms, how to include them both into some nice cobordism, how to interpret them using some nice cobordism category. And I should also mention some calculation about K2. K2, for instance, if you take a field, K2 is generated by symbols AB, where these are AB in K star, subject to suitable relations. And from this viewpoint of forms, you would want to take Q torus and put a copy, just look at the flat bundle with fibers K over it, where monodromy along, let's say monodromy along the meridian is A, monodromy along the longitude is B. Then, for instance, the relation A1, A2B is A1B, A2B can be interpreted as the cobordism where you just split A1, A2 into tutori with A1, A2. So you can kind of see this Steinberg relation, Steinberg symbols, and the relations on them appear as 3D cobordisms between 2D forms with a flat connection. In this case, it's just manifolds. So we have a remark about this, but didn't go beyond this. Yeah, this is sort of this is also I'm using. Also, Anton asked me about maybe applications to mathematical physics. So there is some application of K2 in mathematical physics where people study K2 in the framework of mirror symmetry. So maybe this has some relevance.
People have so in total, right? Okay, so we have two more sports.
You want to go?
I was
You
gonna
want
have
to
you.
go? All right, maybe one more, so we have seven, right? So one more. Which? No, no. 6:15. Point is CEO. It's